on the topic of exponential functions and how we use exponential functions to define some newer functions. The definition of exponential function. So suppose b is a real number. Suppose b is more than 0 and it's never 1. Then for any real number like x, you can define a function y equals to b to the x, and we call this guy exponential function. It's a common mistake for students that they confuse exponential function and power function. Power function is x to power n. This is called power function. When it comes to exponential function, you have some basic properties. The graph of an exponential function, which is defined as f of x equals to b to the x, has the following properties. First of all, if b is more than 1, the graph starts increasing. So you see an increase in the graph. Sometimes we call it exponential growth function. So whenever b is more than 1, like 2 to the x, 3 to the x, 5 to the x, e to the x, and so on, you have exponential growth function. However, if b is bounded between 0 and 1, you have a decreasing function, and sometimes you call it exponential decay function. What's the domain of this function? The domain of the function is negative infinity to positive infinity. It doesn't matter if it's 2 to the x, 3 to the x, 5 to the x, e to the x, or b is more than 1, or it's a half to the x, a third to the x, and so on. If it's exponential decay, the domain is negative infinity to positive infinity. You're allowed to plug in any number that you like for the exponent here. Well, the range, as you can see, is between 0 to infinity. As you can see, the graph never goes to the negative part of y-axis. The y is on the positive part of y-axis. So as you can see, the range is 0 to infinity. Now remember that for infinity, we always use open parenthesis. The line y equals to 0, which is x-axis, is the horizontal asymptote. And number 5, the function passes through the point 0 and 1. Why is that? Because when you plug in 0, b to power 0 is equal to 1. Just a quick note, 0 to power 0 is not 0. That's why we are making sure that b is more than 0. b is never 0. Otherwise, this doesn't work. So these are the basic properties of exponential functions. Exponential functions are one-to-one functions. They have inverse. We're going to talk about inverse of these functions later when we are introducing the inverse of hyperbolic functions. Hyperbolic functions are constructed using exponential functions. Hyperbolic sine of x is denoted by sine hx, which is e to power x minus e to power minus x divided by 2. The graph of this function behaves like this. So the hyperbolic sine has the following behavior. It's increasing function. With the same argument, we can define hyperbolic cosine. Hyperbolic cosine of x is denoted by cosine hyperbolic x, cosine hx, which is e to power x plus e to power minus x divided by 2. the graph of this function behaves like this. It's very similar to a parabola. You can also break these functions and definitions down into other form. So sometimes they write hyperbolic sine of x this way. They say that, hey, this is e to power x minus 1 over e to power x divided by 2. Then on the numerator, they take the common denominator e to the x. You get e to power 2x minus 1 divided by e to the x over 2. And they write it as e to power 2x minus 1 divided by e to power x multiplied by 2. So another way to represent hyperbolic sine is this way. You can do the same thing for the algebra for hyperbolic cosine. Hyperbolic cosine x, which is officially defined as e to the x plus e to power negative x, can be written as 1 over e to power x, then you divide it by 2. On the numerator, take the common denominator, which is e to the x. And then when you multiply e to the x by e to the x, you get e to power 2x plus 1 divided by 2, which in turn can be written as e to 2x plus 1 divided by 2 e to 2x. So these formulas, they are all equivalent to each other. Hyperbolic sine can be written as e to x minus e to power minus x divided by 2, or e to 2x minus 1 divided by 2 e to x. Hyperbolic cosine is e to x plus e to power minus x divided by 2, or equivalently e to 2x plus 1 over 2 e to x. Remember the graph of these types of functions as well. They are very useful. The next set of hyperbolic functions, as you guessed, are hyperbolic tangent and hyperbolic cotangent. Hyperbolic tangent of x is hyperbolic sine over hyperbolic cosine, which is e to x minus e to power minus x divided by e to the x plus e to power minus x. As usual, we can rewrite this using algebra. So hyperbolic tangent can be also written as e to the x minus 1 divided by e to the x over e to the x plus 1 over e to the x. If you take common denominator, you get e to 2x minus 1 divided by e to the x and e to 2x plus 1 divided by e to the x. You can get rid of the common denominator, which is e to the x. So you end up with e to 2x minus 1 divided by e to 2x plus 1. So hyperbolic tangent can be written directly using hyperbolic sine and hyperbolic cosine, or you can write it in simplified version. Hyperbolic cotangent is defined as hyperbolic cosine divided by hyperbolic sine, or e to the x plus e to power minus x over e to the x minus e to power minus x. So now that we know the formula for hyperbolic tangent, we can just use the flip fraction and write this guy as e to 2x plus 1 divided by e to 2x minus 1. So hyperbolic cotangent is defined officially this way. In simplified version, it is e to 2x plus 1 divided by e to power 2x minus 1. Let's take a look at their graphs. The graph of hyperbolic tangent is very similar to inverse tangent that you saw before. And for hyperbolic cotangent, it is divided up into two pieces. So far we introduced 4 important hyperbolic functions. Now the question is, how do we find the rate of change of these functions? How we measure the derivative? So suppose I ask you to find the secant and cosecant as well. Then we're going to take a look at the derivatives. The hyperbolic secant is defined as 1 over hyperbolic cosine. And the hyperbolic cosine, as you remember, is e to the x plus e to power minus x divided by 2. We can flip this and write 2 on the numerator. At the same argument, you can define hyperbolic cosine. Hyperbolic cosecant is 1 divided by hyperbolic sine, which can be written as e to the x minus e to power minus x divided by 2. We can flip 2 and write it on the numerator. So these are the graphs of hyperbolic secant and hyperbolic cosecant. So we introduced 6 important hyperbolic functions. Again, the use of these hyperbolic functions is later in integrals when you're using u sub to calculate the integral of different types of functions. Suppose you're interested in finding the derivative of hyperbolic sine x. Well, we have a nice definition for hyperbolic function. Like in this case, for hyperbolic sine, it's defined as e to the x minus e to power minus x divided by 2. But remember that when you're taking the derivative of e to the x, it is equal to e to the x. When you're taking the derivative of e to power minus x, it is minus e to power minus x. So one by one, we can take the derivative of each one of these and then combine them together. It's equal to e to power x minus minus, which gives you plus e to power minus x, then you divide it by 2. So that's how you find the derivative of hyperbolic sine. But this function is very familiar. This is hyperbolic cosine of x. So the derivative of hyperbolic sine is hyperbolic cosine. Now, what if you want to take the derivative of hyperbolic cosine? To take the derivative of hyperbolic cosine, we do the exact same thing. We use the direct definition. We are taking the derivative of e to the x plus e to power minus x divided by 2, and we follow the same sets of formulas. The derivative of e to the x is e to the x, and the derivative of e to power minus x is minus e to power minus x. This guy in turns can be written as e to the x minus e to power minus x divided by 2, which we already know is hyperbolic sine of x. So remember that in calculus, when we have sine of x, we take the derivative of sine of x, it is equal to cosine of x. And when you're taking the derivative of cosine of x, it happens to be minus sine of x. But pay attention here, when it comes to hyperbolic functions, the behavior is different. What we see here is, if I take the derivative of hyperbolic sine of x, it becomes hyperbolic cosine of x. And when I take the derivative of hyperbolic sine cosine of x, it's exactly the same as hyperbolic sine without any negative sign in front of it. Okay, let us take a look at other functions and their derivatives. So we just saw that when we are taking the derivative of hyperbolic sine, it is nothing but hyperbolic cosine. We saw that the derivative of hyperbolic cosine is hyperbolic sine. What is the derivative of hyperbolic tangent of x? it is equal to hyperbolic secant to the second power. And we can just basically do the exact same thing that we did before and calculate this derivative. So what was the definition of hyperbolic tangent? When we are taking the derivative of hyperbolic tangent, we are taking the derivative of e to the x minus e to power minus x divided by e to the x plus e to power minus x. So here we're going to apply the quotient rule. What you're going to do, you're going to take the derivative of e to the x minus e to power minus x times e to the x plus e to power minus x minus, you're going to copy down e to the x minus e to power minus x, and then take the derivative of the denominator, which is e to the x minus e to power minus x, and divide everything by the denominator to the second power, e to the x plus e to power minus x to the second power. Perfect. So this guy can be written as, let me just write it on top here. The derivative of the first quantity is e to the x plus e to power minus x times e to the x plus e to power minus x minus e to the x minus e to power minus x times the derivative, which is e to the x plus e to power minus x. Okay, we should have taken the derivative of this guy, am I right? Oh, this should be plus. Okay, perfect. So now we end up with a negative sign, so you get exponent 2. And divided by e to the x plus e to power minus x to the second power. So what happens here, we can basically distribute e to the x into parentheses, e to power minus x into parentheses, do the same thing here, and try to simplify as much as you can. So this guy in turns can be written as, so here you have e to 2x, and then plus e to power 0, and then plus another e to power 0 plus e to power minus 2x minus, so let me put this in parentheses, e to power 2x minus e to power 0, and let's see, minus e to power 0, and then you get plus e to power negative 2x, and on the denominator you have the same thing, e to the x plus e to power minus x to the second power. If you distribute negative sign into parentheses, e to 2x and negative e to 2x, they get canceled out. E to negative 2x and negative e to power negative 2x, they get canceled out. So you're left with, you have a 2 here, and you have another 2 here. So 2 plus 2 is 4, divided by e to the x plus e to power minus x to the second power. But this guy can be written as 1 over e to the x plus e to power minus x divided by 2 to the second power. But this is by definition, as you remember, the definition of your secant. The secant is 1 divided by e to the x plus e to power minus x divided by 2. So this guy is 1 over secant, hyperbolic secant to the second power of x. So that's how you end up with, let me make sure I wrote down everything correctly. Yeah, this is 1 divided by, okay, you get the whole thing down here. This is basically your hyperbolic secant to the second power. So this is the algebra behind this, okay?